All right, let's dive right in. Today, we are talking about something that sounds like science fiction, but is actually ancient history. We're looking at these incredible, almost forgotten ways to create solid stone, methods that could completely shake up the entire modern construction industry as we know it. So let me just start with a question. What if I told you that you could take regular loose sand and turn it into solid, load-bearing stone for less than $6? No cement trucks, no giant mixers, and definitely no kilns burning at thousands of degrees. You'd probably think that's impossible, right? Well, not only is it possible, it's been happening for, well, forever. To get why this isn't everyday knowledge, you gotta understand the sheer scale of what it's up against. This number, $400 billion. That's how much the global cement industry makes every single year. This is the Goliath in our story, a massive industry built on one very specific and extremely profitable product. So here's our game plan for this explainer. We're going to start with the fundamental problem with modern concrete. Then we'll explore three absolutely mind-blowing alternatives, making stone with electricity, with biology, and with some super simple chemistry. After that, we'll look at the massive walls standing in the way of these ideas before we wrap it all up with how this knowledge is actually hiding in plain sight. Okay, first things first, the concrete problem. And this isn't just about pollution. It's about a deep, fundamental issue that's literally baked into the chemistry of how we build our entire world. You know, we hear a lot about the carbon footprint of flying, right? Well, get a load of this. Producing Portland cement is responsible for a staggering 8% of all global CO2 emissions. That is more than the entire aviation and shipping industries combined. Think about that. If the cement industry were its own country, it would be the third biggest polluter on Earth. And here's the real kicker. This isn't a problem we can just solve by switching to green energy. The problem is the chemistry itself. See, to make cement, you have to heat limestone up to insane temperatures. That process, it's called calcination, and it chemically rips the limestone apart. And a byproduct of that reaction is always, you guessed it, carbon dioxide. You just can't make Portland cement without making CO2. It's unavoidable. But what if we could just bypass that whole chemical process? This brings us to our first alternative, creating stone from electricity. A method, by the way, that nature's been using since the first lightning bolt hit a sandy beach. The official name is electromineralization. Basically, you pass a very low voltage electric current through wet sand. That current kicks off a reaction, causing minerals that are already dissolved in the water to crystallize and grow in the spaces between the sand grains. It is literally growing solid stone inside the sand, walking everything together at a molecular level. And this idea, it's not new at all. The ancient Greeks and Romans saw these glass tubes in the sand after thunderstorms, we now call them fulgurites, and thought they were sacred. By the 1930s, engineers were using a similar concept to make the ground stronger for dams. Then in '76, an architect patented seacrete, a way to literally grow building material in the ocean. And just this year, scientists at Northwestern confirmed a method that costs just $3 to $6 and uses less voltage than a couple of AA batteries. And let me tell you why that cost matters so much. The normal way to do this, to stabilize soil, is to inject a bunch of chemical binders. That can cost you up to $70 per cubic meter. This electrical method, it gets you the same result for a tiny fraction of that. We're talking less than a tenth of the price, using pretty much just salt water and a trickle of electricity. Alright, so from electricity, we're now moving to biology. This next method uses an actual living thing to create stone and even repair it. It's time to talk about the self-healing brick. It's called bio-cementation, and it all comes down to a common little microbe found in soil, Sporosarcina pasteurii. This bacteria is a tiny factory. It produces an enzyme that, when it comes into contact with a simple solution, triggers a reaction that creates pure limestone, right there, room temperature, gluing sand particles together from the inside out. But here's where it gets really wild. The bacteria can just hang out dormant inside the stone for years. If a tiny crack forms and a little water gets in, they wake up and start making new limestone, sealing the crack shut all by themselves. It's a material that automatically repairs itself. I mean, that idea alone completely turns the modern business model of things breaking and needing to be replaced on its head. And don't for a second think this stuff is fragile. Biocement isn't just a cool green idea. It's often stronger. In lab tests, it consistently hits a compressive strength of 4,000 psi or even more. Your standard residential concrete, that's usually rated for around 3,000 psi. So yeah, the bacteria win. And here's the best part. It's so simple. The ingredients are just regular sand, agricultural urea, which is basically fertilizer, and the bacteria culture, which you can just buy online. You mix it up with water, pour it over the sand, and in about 2 or 3 days, boom, solid stone. Okay, our third and final method is maybe the oldest and most powerful one of them all. It's a type of cold fusion chemistry that ancient civilizations seem to have completely mastered thousands of years ago. It's called geopolymerization. And it sounds complex, but it's not. If you take a simple acid, like the kind in household vinegar, and mix it with the right kind of sand, it kicks off this amazing reaction. The acid yanks silicon and aluminum ions out of the sand, and they immediately snap back together into a new, incredibly dense, rock-solid network. It's actually a similar type of chemistry used to make the heat shields on spacecraft. And this timeline, this just shows you how powerful this chemistry is. There's real evidence the ancient Egyptians used a liquid stone slurry like this to cast the giant blocks for the pyramids. We know the Romans made concrete with volcanic ash that actually gets stronger over time in salt water. And the H-blocks at Pumapunku in Bolivia, with their impossible precision, they look like they were cast, not carved. Now fast forward to today, and NASA is testing this exact same method to build stuff on the moon, getting strengths up to an incredible 15,000 psi. So this leads us to the big obvious question, right? If these methods are so cheap, so strong, and so good for the planet, why on earth isn't our world built with them? Why are we still stuck on Portland cement? Well, it turns out the hurdles aren't technical, they're economic, and they're structural. I mean, building codes have been written around Portland cement for 100 years. That's a ton of inertia. Plus, you can't exactly patent sand or bacteria or vinegar, so there's no big profit incentive for a corporation to push it. A product that heals itself and lasts for centuries, that kills the whole business model of things breaking and needing to be replaced. And finally, the existing global cement industry is it's a behemoth. It's too big to turn on a dime. So where does all this leave us? Well, it leaves us with this incredible knowledge that hasn't been locked away in a secret vault. It's just been buried in plain sight. And this chart just lays it all out, clear as day. On one side, you've got Portland cement, a huge carbon emitter, needs tons of energy, it's expensive, and it's basically designed to fall apart after 50 or 100 years. And on the other side, you have these alternatives, practically zero emissions, room temperature processes, unbelievably cheap, and a durability that we measure in centuries, not decades. The choice seems pretty obvious. One of our sources really hit the nail on the head. This information was never lost. It's been sitting there the whole time, in scientific journals, in old texts, and in nature itself, just waiting for people to get curious and start looking for it. And now, you're one of those people. You know. So I'll just leave you with this final thought. If these powerful, simple solutions for one of our world's biggest industries were hiding in plain sight this whole time, it really makes you wonder, doesn't it? What other amazing, forgotten solutions are out there, just waiting for us to rediscover them? Thanks for joining me.